Welcome back to another episode of Second Career Pilot. Today we're zeroing in on something absolutely fundamental for those of you just starting out in visual flight roles: navigation. Think of this as your essential guide to confidently and safely getting your aircraft from, well, point A to point B.
Exactly. We're going to break down the core ideas behind planning and executing cross-country flights when you're flying just by looking outside, basically.
Visual references.
Right, visual references. And we'll be drawing on well-established aviation knowledge, things like the pilot's handbook of aeronautical knowledge, to give you a clear, practical understanding.
Okay, let's jump right in. At its heart, air navigation is simply, well, knowing how to pilot your aircraft from one place to another while keeping a clear picture of where you are the whole time. Sounds simple, maybe?
It does, but like anything in aviation, there's some key elements to really get familiar with.
Right.
And it all starts well before you even get near the airplane.
Mm-hmm.
Pre-flight planning. This is where you map out your path on an aeronautical chart. You pick out landmarks you can spot easily.
Checkpoints.
Checkpoints, yeah. You figure out the distances, get the latest weather, of course, and then use all that to calculate flight time, headings, and critically, how much fuel you'll need. It's really the groundwork.
So like planning a road trip, but maybe with a bit more precision needed and higher stakes.
Definitely more precision. Absolutely. Now, when you're actually flying VFR, there are three main ways pilots navigate.
Okay, what are they?
First up is pilotage. This is probably the most intuitive one for new pilots. You're just navigating by looking at visible landmarks on the ground.
Like lakes, towns?
Exactly. Lakes, towns, rivers, highways.
Yeah.
And matching them up with what's on your chart. See a big river bend. Find it on the chart. Helps confirm you are where you think you are.
Makes sense. Using what you see. What's number two?
Second is dead reckoning. This one's a bit more involved. It relies on calculations using your direction and the distance you think you've flown from a known starting point.
Calculations. So based on airspeed. Time.
Right. Airspeed, time flown, your heading. You use those to estimate where you should be. It stands for deduced reckoning, actually.
Ah, okay. So keeping track of speed, time, heading to figure out position. And the third?
The third method is radio navigation, using radio aids like VORs or GPS, and the equipment in your plane to figure out where you are or follow a specific path. We can touch on those basics a bit later.
Gotcha. Pilotage, dead reckoning, radio nav. Now, you mentioned aeronautical charts. For a VFR pilot, these are really the foundation, the roadmaps for the sky, aren't they?
Absolutely are. Essential. Aeronautical charts are packed with crucial information. Helps you track your position, stay safe, avoid airspace you shouldn't be in, all that stuff.
And there are different types, you mentioned.
Yep, three main types you'll deal with in VFR flight.
Okay, what are the differences?
The most common are sectional charts. Scale is 1 to 500,000. That means 1 inch on the chart is about 6.86 nautical miles.
So pretty detailed.
Yeah, very detailed. Shows airports, navades, airspace boundaries, terrain features, obstacles, loads of info. And they're updated usually every 6 months in the U.S. Some areas might be annual, but mostly semi-annually. Got to have current charts.
Okay, sectionals. Updated often, lots of detail. What's next?
Next are VFR terminal area charts, or TAC charts. Think of these for flying near busy Class B airspace, like around major cities and airports.
Ah, so even more detail.
Exactly. The scale is larger, 1 to 250,000, so 1 inch is only about 3.43 nautical miles. Gives you that finer detail you need in complex, busy airspace. Also revised semi-annually, mostly.
Makes sense for busy areas. And the last one.
Lastly, there are World Aeronautical Charts, or WACs. These cover larger areas, scale is 1 to a million. So 1 inch is almost 14 nautical miles.
Less detail then.
Right, less detail because of the smaller scale. Uses similar symbols to sectionals, but you just don't get the same level of granularity. Good for planning longer flights, maybe, or for faster aircraft, usually updated annually.
Good to know the differences. And if someone needs to get these charts.
The FAA actually has a free catalog online. You can find it on their aeronautical navigation products website, aeronon.faa.gov, I believe. It lists all the charts and how to get them.
Great resource. Now, these charts, they look pretty busy, symbols everywhere. How do you start to, make sense of it all?
The key is the chart legend. It's printed right on the chart, usually on one of the side panels.
The decoder ring.
Exactly. It explains what all the symbols, colors, and lines mean. Airports, navades, airspace types, obstacles. It's all defined in the legend. You absolutely need to study that legend and refer back to it. And pay close attention to specifics on the chart itself, like ATC frequencies and airspace details.
Okay, so become best friends with the legend. Got it. Stepping back from the charts, How do we pinpoint location using more basic geography, latitude and longitude?
Right, back to basics. Latitude lines or parallels run east-west. They measure your position north or south of the equator, which is your degrees latitude. North pole is 90 north, south pole 90 south.
Mhm.
Longitude lines, or meridians, run north-south from pole to pole. They measure your position east or west of the prime meridian, which runs through Greenwich, England. That's 0 degrees longitude, and it goes up to 180 degrees east or west. Think of it like a grid on the globe.
A global grid. Can you give an example, like where's Chicago on that grid?
Sure. Chicago is roughly 42 degrees north latitude and about 88 degrees west longitude. Washington, D.C. is around 39 north, 77 west. Any point on Earth has unique coordinates.
That helps picture it. Now, these longitude lines, the meridians, they're tied into time zones too, right?
Yes, absolutely. The Earth spins 360 degrees in 24 hours, right?
Right.
So that's 15 degrees of longitude every hour. Time zones are generally based around these 15-degree intervals.
And in the mainland U.S., we have the four main ones.
Correct. Eastern, Central, Mountain, and Pacific, roughly centered on the 75th, 90th, 105th, and 120th meridians west. The boundaries wiggle a bit for practical reasons, but that's the basis.
And aviation uses that 24-hour clock format, I hear, 1300 instead of 1 p.m.
Yes, always. It avoids confusion. Is it 8 a.m. or 8 p.m.? With a 24-hour clock, 0800 is morning, 2000 is evening. No ambiguity. Especially crucial when dealing with flight plans, ATC, weather reports across different time zones.
Makes total sense. And that brings us to UTC, or Zulu time. What's that about?
Universal Coordinated Time, UTC or Zulu time.
Oh.
They all mean the same thing. It's the worldwide standard time reference for aviation. It's basically the time at the prime meridian, 0 degrees longitude.
Why use a universal time?
Because flights often cross multiple time zones.
Sure.
Imagine the confusion trying to coordinate everything using local times. Weather reports, flight plans, ATC clearances. They're all based on UTC for consistency.
Okay, so how do we convert local U.S. time to UTC?
You add hours. For Eastern Standard Time, add 5 hours. Central Standard, add 6. Mountain Standard, add 7. And Pacific Standard, add 8 hours.
Simple enough.
But remember Daylight Saving Time. When DST is active, you add 1 hour less. So Eastern Daylight Time is UTC minus 4 hours, not 5. You always need to check if DST is in effect.
Right, that DST adjustment is important. Okay, fundamental skill. Now let's switch to direction. Charts use true north, but the compass points to magnetic north. Big difference, right?
Huge difference and critical to understand. True north, TN, is the direction to the geographic North Pole. All those longitude lines on your chart point to true north. Your intended path on the chart is measured relative to true north. That's your true course. Do you see?
Oh, okay. But the compass?
But your aircraft compass is magnetic. It aligns with the Earth's magnetic field, pointing towards magnetic north, MN. And magnetic north isn't in the same place as true north. It's actually off somewhere in northern Canada and wanders around a bit.
They don't line up.
Nope. The angular difference between true north and magnetic north at any given location is called magnetic variation.
Variation?
Yes. And it's different depending on where you are on Earth.
Yeah.
On your chart, you'll see these dashed magenta lines.
The isogonic lines.
Exactly. Isogonic lines. They connect points that have the same magnetic variation. The chart tells you whether the variation is east or west and by how many degrees. There's also one line, the agonic line, where variation is 0.
So we have true course from the chart, but we need magnetic course for the compass. How do we convert?
You have to apply the variation. There's a simple rule, a mnemonic. East is least, west is best. If the variation is east, you subtract it from your true course. If the variation is west, you add it to your true course. That gives you your magnetic course.
Okay, east is least, subtract, west is best, add.
Got it.
So true course corrected for variation gives magnetic course. Is that what we fly on the compass?
Almost. One more step. There's something called compass deviation.
Deviation, what's that?
Deviation is error caused by magnetic fields within your specific aircraft. Things like the engine, radios, electrical circuits, all the metal stuff in and around the cockpit can pull the compass needle slightly away from magnetic north.
Ah, so each plane has its own little magnetic quirk.
Pretty much, yeah. And the amount of deviation can actually change depending on which direction the aircraft is heading.
So how do we account for that?
Every aircraft should have a compass deviation card mounted near the compass. This little card lists the specific correction you need to apply for various magnetic headings. It'll say something like, for N steer 002 or for E steer 093. You find the correction for your calculated magnetic heading and apply it.
So apply the correction from the card to the magnetic heading.
And that gives you your compass heading, CH. That's the final number you actually want to see on your compass dial to fly the intended magnetic course.
Okay, let's recap that sequence. Start with true course from the chart, adjust for local magnetic variation, east subtract, west add, to get magnetic heading. Then adjust that using the plane's compass deviation card to get the final compass heading.
You got it.
Yeah.
That's the process. And often we think about it in terms of heading, which includes wind correction. So it's true course, TC, plus or minus wind correction angle,
Yeah.
TA, gives true heading, PH. Then true heading, TH, plus or minus variation V, gives magnetic heading, MH. And finally, magnetic heading, MH, plus or minus deviation D, gives compass heading, CH. TCO is THFEMH.
Right. The wind correction, you mentioned that. Let's talk wind. It's nearly always windy up there, isn't it? How does it mess with our navigation?
Oh, it definitely affects things. Wind is just a moving mass of air. So the airplane is moving through the air mass, but the air mass itself is moving over the ground.
So airspeed versus ground speed.
Exactly. Airspeed is your speed relative to the air. Ground speed, GS, is your actual speed over the ground. They aren't always the same.
Headwinds slow you down over the ground.
Right. A headwind reduces your ground speed.
Right.
A tailwind, wind from behind, increases your ground speed. And a crosswind, wind from the side,
Pushes you sideways. Drift.
causes drift, correct. Your heading is where the nose is pointed. Your track is your actual path over the ground. If there's a crosswind, your heading and track won't be the same. The difference is the drift angle.
So to actually fly our intended course over the ground in a crosswind, we can't just point the nose along the course line?
Nope. You have to angle the nose slightly into the wind. That correction angle is called the wind correction angle, or WCA.
The WCA.
You calculate the WCA needed to counteract the drift so that your resulting track over the ground matches your desired course. Figuring out that WCA is a key part of flight planning and dead reckoning.
Okay, crucial calculation. Speaking of calculations, there must be some basic formulas pilots use all the time for speed, distance, time.
Absolutely. The core relationships are fundamental. Time equals distance divided by ground speed, TS DGS.
Okay,
Distance equals ground speed multiplied by time, D equals GSXT.
makes sense.
And ground speed equals distance divided by time, GS equals DT. You'll use these constantly.
Seems straightforward. And often time is in minutes, but formulas might need hours.
Right. Easy conversion. To go from minutes to hours, just divide by 60. So 45 minutes is 4560, or 0.75 hours.
And hours to minutes.
Multiply by 60. So 1.5 hours is 1.5 times 60 equals 90 minutes.
Got it. And knots versus miles per hour. Aviation uses knots mostly.
Mostly, yes. A knot is 1 nautical mile per hour. A nautical mile is a bit longer than a statute mile, about 1.15 statute miles. So to convert knots to multiply by 1.15, 100 knots is about 115 per hour. Your flight computer, especially electronic ones, can handle these conversions easily.
Okay, good to know. Another critical planning piece, fuel. How do we figure out fuel needs?
Super critical. For most piston engine trainers, fuel consumption is measured in gallons per hour, GPH.
And that number comes from?
The official source is always your Aircraft-Specific Pilot's Operating Handbook, POH, or the Aircraft Flight Manual, AFM. It will have charts or tables showing fuel burn rates at different altitudes, power settings, and temperatures. You must use the numbers for your specific aircraft.
Never guess.
Never guess. So to calculate fuel needed for the flight itself, you take your estimated flight time, which depends on your ground speed, remember, so wind matters, and multiply it by the GPH rate from the POH for your planned cruise settings.
But that's just for the cruise portion, right? We need more.
Absolutely. That calculation gives you the fuel just for the trip. You must add reserve fuel. Regulations require it, and common sense demands it. You need fuel for engine start, taxi, takeoff, climb, which often burns more fuel, plus a safety margin for unexpected delays, navigation errors, or needing to divert. Never plan to land on fumes.
Always have reserves. Good advice. Now, with all these calculations, time, speed, distance, heading, fuel, what tools help pilots manage all this?
The classic tool is the mechanical flight computer, often called an E6B. It's basically a circular slide rule.
Looks intimidating.
It can look that way at first, but it's incredibly powerful for solving all these wind problems, speed, time, distance calculations, fuel burn, density, altitude, lots of stuff. Takes practice, but it works without batteries.
True. Any other tools?
Yes, the plotter. It's essentially a protractor and ruler combined, made of clear plastic. You use it directly on the chart to measure the true course of your flight path and to measure distances using the chart's scale. Plotter gets the raw data off the chart. E6B, or an electronic calculator, crunches the numbers.
Plotter and E6B, the dynamic duo of VFR planning. Okay, let's circle back to pilotage. We said it's navigating by landmarks. Any more tips for doing it effectively?
Sure. When selecting checkpoints, pick things that are really prominent and unlikely to be confused with something else. Big highway intersections, uniquely shaped lakes, distinct towns. Power lines can be good, but be aware of their height.
Good point.
Also, try to use bracketing features, things like roads, rivers, or railroads that run roughly parallel to your course, either to the left or right. If that road that's supposed to be on your left drifts underneath you or to your right, you know you're drifting off course. It helps you stay in the corridor.
Like lane markers.
Kind of, yeah. And don't rely on just one checkpoint. Pick several along the route. If you miss one or aren't sure, keep flying the heading and look for the next one. Don't fixate. Remember the chart scale when judging distances. An inch on a sectional is almost 7 nautical miles. Things could look closer than they are. And be aware of new construction not yet on the chart, or things like antennas that can be hard to see.
Good cautions. So pilotage is visual confirmation. What about dead reckoning again? How does that fit in for a VFR flight?
Dead reckoning, remember, is navigating just by calculations. Time, speed, heading, adjusted for wind. In practice, for VFR, you rarely use only dead reckoning.
You combine it with pilotage.
Exactly. It's almost always used with pilotage. You use dead reckoning calculations based on forecast winds and your planned airspeed to figure out your initial heading, including the WCA, and your estimated ground speed and time between checkpoints. That's your plan. Then, as you fly, you use pilotage spotting those checkpoints to confirm you're actually on course and on time. If you see you're drifting or reaching checkpoints earlier or later than planned, you adjust your heading or recalculate your ground speed based on what you're actually seeing. They work together. DR sets the plan, pilotage keeps it real.
That makes sense. They complement each other. Now, you mentioned the wind correction angle comes from figuring out the wind's effect. The wind triangle is related to that.
Yes, the wind triangle is the graphical way to visualize and solve the wind problem. It's a vector diagram.
Okay, vectors. Sounds like geometry.
It is, but it's straightforward. You have 3 vectors, 3 arrows representing direction and speed. One represents your aircraft's heading and true airspeed. Another represents the wind's direction and velocity. The third, the resultant vector, represents your actual track over the ground and your ground speed.
So it shows how the wind pushes you.
Precisely. By drawing these vectors to scale, usually on the back of your E6B or using a dedicated worksheet, you can measure the third side to find your ground speed, and you can measure the angle needed to offset the wind, which is your wind correction angle, WCA. It lets you figure out the heading you need to fly, true heading, to achieve your desired true course.
So a visual tool for calculating heading and ground speed. Now, putting this all together, flight planning. You said it's legally required for the pilot to be familiar with all available info.
Absolutely. 14 CFR Part 91. Before any flight, not just cross-country, the pilot in command must be familiar with weather, fuel requirements, alternate airports if the flight can't be completed as planned, and any known traffic delays. It's serious stuff.
No shortcuts. What materials do you need to gather for planning?
You need current charts for the whole route, plus maybe adjoining ones just in case. Your plotter, your flight computer, E6B or electronic, pencils, flight log sheets, and crucially, the AFMPOH for your specific aircraft. Maybe a flashlight, water, survival gear, depending on the flight.
And check weather early.
Definitely. Get a weather briefing early. See if the flight is even feasible. Wind, clouds, visibility. It affects your route, your altitude, everything. Use flight service or approved online sources.
Okay. What about info on the airports themselves?
You need to dig into that. Check the Chart Supplement U.S. used to be called the Airport Facility Directory, or AFD.
What's in there?
Tons of vital info. Airport location, elevation, runway details, length, surfaces, lighting, available services like fuel, radio frequencies, notes about noise abatement or local procedures. Really important stuff. And always check NOTAMs, notices to airmen, for any recent temporary changes like runway closures, taxiway work, Navade outages.
Don't forget NOTAMs. And the POH again?
Yes, back to the POH. You need it for weight and balance calculations, making sure the loaded aircraft is within limits. And for performance calculations, takeoff distance, landing distance needed based on weight, altitude, temperature. Of course, those fuel consumption numbers for your planned power setting and altitude.
Wow, okay. A lot goes into planning. Can we walk through the steps of actually plotting the course on the chart? Say, Chickasha to Guthrie in Oklahoma, like the example in the handbook.
Sure. First step, draw the line. Use your plotter's straight edge to draw a light pencil line directly from the center of Chickasha Municipal Airport to Guthrie Edmond Regional Airport. That's your course line.
Line drawn. Then checkpoints.
Yep. Look along that line and pick out easily identifiable checkpoints, maybe every 15, 20 miles or so. Maybe a town like Union City, the crossing of the North Canadian River, maybe Wiley Post Airport as you get closer. Mark them lightly on the course line.
Okay, checkpoints marked. Now airspace and terrain.
Right. Scan along and near your course line. Notice Will Rogers World Airport, OKC, is nearby. That's Class C airspace. Wiley Post, PWA, is Class D. You need to know the dimensions and rules for that airspace. Look at terrain features, any tall towers. The chart shows elevations. In that example, there's a tower reaching 2,749 feet MSL and terrain up to 2,900 feet MSL west of the course.
So watch out for those. Altitude selection next.
Based on terrain, obstacles, and airspace, pick a cruising altitude. For VFR eastbound above 3,000 feet AGL, you need an odd 1,000 plus 500 feet altitude, like 3,500, 500, 500, etc. Let's say we pick 5,500 feet MSL for this trip, well above obstacles and terrain, and clears the Class C and D airspace vertically.
5,500 feet MSL. Now measure distances.
Use the plotter's nautical mile scale, matching the sectional chart, to measure the total distance from Chickasha to Guthrie. Also measure the distance between each checkpoint you selected. Write these down on your flight log.
Okay, distance is noted. How about the true course?
Place the plotter's grommet, the little hole, over a meridian longitude line near the middle of your course line. Align the plotter's edge with your course line. Then read the direction where the meridian passes onto the plotter's protractor scale. Let's say it reads 031 degrees. That's your true course.
031 true course. Now we need compass heading. Back to that formula.
Right. Now you need wind information for 5,500 feet. Let's say the forecast wind is 360 at 10 knots, and your true airspeed from the POH for 5,500 feet is 110 knots. You use your E6B or calculator to find the wind correction angle and ground speed.
Okay.
For this example, let's say the calculation gives you a WCA of 3 degrees left, so subtract 3, and a ground speed of 106 knots. So true course 031 minus 3 WCA gives a true heading of 028 degrees.
TH is 028, now variation.
Look at the isogonic line near your route on the chart. Let's say it shows 7 degrees east variation. Remember, east is least. So true heading 028 more to 7 east variation gives a magnetic heading of 021 degrees.
MH is 021, last step, deviation.
Check the deviation card in your specific aircraft for heading year 021. Let's pretend the card says to add 2 degrees plus 2 for that heading range. So magnetic heading 021 plus 2 deviation gives a final compass heading of 023 degrees.
Compass heading 023, that's what we steer.
That's the goal. Now use that calculated ground speed, 106 knots, and the total distance to figure out your total flight time. Distance divided by GS. And use that flight time multiplied by your POH fuel burn rate, say 6 GPH, to calculate fuel needed. Add your reserve fuel to that. Record everything on your flight log.
Phew. Detailed, but logical. Flight log keeps it organized.
Now, about filing a VFR flight plan. Not required, but recommended.
Highly recommended. It's a safety net. If you don't arrive reasonably close to your estimated time of arrival and haven't closed your flight plan, Flight Service will initiate search and rescue procedures. It tells people where you were going and when you expected to get there.
How do you file one?
Easiest way is usually to call Flight Service, 1-800-WX-BRIEF, before you leave. You can also file online through various services or sometimes by radio after takeoff, but calling ahead is generally best.
What info do they need? Your aircraft type and ID number. Equipment suffix, like G for GPS. Your true airspeed. Departure point, proposed departure time in UTC. Cruising altitude, you can just say VFR or specify like 5,500. Your route, direct or via checkpoints. Destination, estimated time en route. Fuel on board in hours and minutes, pilot info, number of people on board.
Okay, and the most important thing after landing.
Close your flight plan. Absolutely critical. Call Flight Service back or use an online service to close it. If you don't, they will start looking for you, assuming you crash. Don't forget.
Don't be that person. Got it. Okay, so that's planning. Let's briefly touch on those radio navigation systems again, just the basics.
Right. As a supplement to Pilotage and Dr. main ones for VFR are VOR, NDB, and GPS.
VOR first. VHF omnidirectional range.
Yep. Ground stations transmit signals that let your receiver figure out your magnetic bearing from or to the station. These bearings are called radials, like 360 spokes from a wheel hub.
VHF, so line of sight.
Yes. Limited by line of sight. Higher you are, the further you can receive it. Each VOR has an identifier, Morse code, or voice, so you know you've tuned the right one.
And in the cockpit, you use the CDI.
Usually, yes. The course deviation indicator. You tune the VOR frequency, then use the OBS knob omnibearing selector to pick a radial. The needle shows if you're left or right of that radial, and the tow from flag tells you if that radial leads toward or away from the station. You can use it to track directly to or from a VOR, or determine your position by seeing which radial you're on.
Useful for tracking a course. Okay, NDBs, non-directional beacons.
These use lower frequency signals, LFMF band, and an ADF receiver in the plane automatic direction finder.
Lower frequency, different characteristics.
Right. Not line of sight limited. Signals can follow the Earth's curve better, so range can be greater, especially at low altitude. But they're very prone to interference from thunderstorms, electrical noise, even shoreline effects. Can make the needle erratic.
And the ADF instrument.
The needle on the ADF indicator simply points towards the NDB station, relative to the nose of the aircraft. So if the needle points straight ahead, 0 degrees relative bearing, the station is directly in front of you. If it points to the right wing tip, 90 degrees, the station is off your right. Simpler in concept, but takes practice to use effectively for tracking.
Points to the station. Got it. And finally, GPS. It's everywhere now.
Global positioning system, satellite-based, gives you precise position anywhere, anytime, usually. It's an RNAV system area navigation, meaning you can navigate point to point without needing to fly directly towards or away from ground stations.
Sounds powerful. Any VFR-specific considerations?
This is definitely. First, don't become solely reliant on it. Always back it up with Pilotage, DR, maybe VORs. Understand its limitations.
It's like RAIM.
Yes. Receiver Autonomous Integrity Monitoring. That's the GPS system, checking itself for accuracy. Not all basic VFR GPS units have RAIM alerting, so you might not know if the signal is unreliable. Also, database currency is huge. If you're using it for airspace awareness or navigating to specific waypoints, the database must be up to date. Outdated databases can be dangerous.
Keep it current. What about VFR waypoints?
These are points defined in the GPS database, often with names starting VP, specifically for VFR use. They can help with situational awareness or defining informal routes, but they aren't for IFR navigation and should be loaded pre-flight.
Okay, GPS is great, but use it wisely and keep it updated. Now, what if, despite all this planning and these tools, a pilot gets, well, lost or at least unsure of their position?
Heavens, first thing, don't panic, fly the airplane. Standard advice is often summarized by the 5 C's. Climb, communicate, confess, comply, conserve. Climbing generally gives you better visibility to spot landmarks, better reception for radios and navaids, and keeps you further from unseen obstacles.
Communicate and confess.
Use your radio. Talk to air traffic control, any nearby tower, approach control, or center frequency you can find on the chart, or even flight service. Tell them you're unsure of your position. Confess. They have radar and direction-finding equipment and can often help locate you. Don't be embarrassed. Safety first.
Comply.
Follow any instructions ATC gives you. They might give you vectors, headings to fly, to get you back on course or to an airport.
And conserve.
Conserve fuel. Lean the mixture appropriately. Fly at an efficient speed. While you're doing this, try to identify features below. Use VORs or GPS to get a fix if possible. If things get really critical, don't hesitate to use the emergency frequency 121.5 MHz and set your transponder to 7700.
Good practical steps. What about needing to divert, change plans mid-flight?
Diversions happen too. Maybe unexpected weather pops up, or you have a minor mechanical issue, or maybe you just realize you underestimated fuel needs. Good risk management means being ready to divert.
So plan for alternates.
Absolutely. During pre-flight, identify potential alternate airports along your route. If you need to divert, pick the best option based on conditions and your situation. Turn towards it promptly. You can often approximate a course by looking at a VOR compass rose on the chart or nearby airways.
Then recalculate.
Once you're heading towards the alternate, note the time. Use your best estimate of winds aloft to figure out a new heading, ground speed, arrival time, and fuel required. Priority 1 is always flying the aircraft safely, but delegate attention to the navigation and planning as needed. Don't delay a necessary diversion.
Sound advice. Fly the plane first. Well, this has been a really thorough overview of VFR navigation essentials.
Yeah, there's a lot there, but it breaks down into logical steps. It really boils down to planning your flight and then flying your plan while continuously monitoring your progress using pilotage, maybe some dead reckoning, and your available navaids.
Thorough planning, skillful execution, and using all the tools available. That seems to be the key takeaway for safe VFR flight.
Couldn't have said it better myself. It's about building those skills and applying them diligently on every flight.
Thanks for listening.